Hello, now that we have some results about circles and some different things related to circles like inscribed angles and different things like that, and some more results about similar triangles, let's go back to look at quadrilaterals again. And specifically, I want to look at some cyclic quadrilaterals. So here's my large GeoGebra collection of quadrilaterals. If we click on circle relationships, we can talk about cyclic quadrilaterals here. And a cyclic quadrilateral, by definition, is one in which there is a circumscribed circle. Now, one of the things that we know about cyclic quadrilaterals or cyclic polygons in general is that if this is going to have a circle that circumscribes the polygon, that is, a circle that contains all of the vertices of the polygon, then the perpendicular bisectors of the sides are all going to have to meet at a single point. And it's pretty easy to see why this is true. Um, if you have, we proved earlier that a perpendicular bisector, say this side AD here, is the set of points that are equally distant from A and D. Well, if there's going to be a circle going through A and D, it's going to have to be on that line. Well, if likewise the perpendicular bisector here of side AB, if it's going to have a circle going through A and B, it's also got to be on that line. Now, one of the on this perpendicular bisector, and of course that means it has to be where these two things intersect. Now, one thing that's interesting that we proved about triangles is that all triangles are cyclic, so we can always make a circle that hits the three vertices of any particular triangle. But for quadrilateral, there's no guarantee that that fourth vertex there uh, is going to be on there. But if the perpendicular bisectors of all the sides meet at the same point, then that point is equally distant from all of the vertices. So it will be this what we call the circumcenter, the center of the circumscribed circle. Now, there's also some interesting things when we look at some angles here. Okay, and uh, maybe not so obvious when we look at these numbers here, but look what happens when we add this one together. Let's say add 1.26 and 1.88. What do you get? 3.14. Does that sound familiar? Yeah, that's pi. These are supplementary here. Okay, so these are supplementary angles here and here. They add up to pi, or if we did degrees, they would add up to 180 degrees for both pair. Well, how can we see that? Well, now that we know something about inscribed angles, we can see that each of these angles that are our angles of our quadrilateral, our interior angles of our quadrilateral, each one of those is an inscribed angle in the circle. So let's just take, say, angle A and angle C. Well, angle A is going to intercept this arc that goes from B to C to D, and angle C is going to intercept the arc that goes from B to A to D. Okay, so each of these is half the measure of the intercepted arc. So angle A is half the measure of the angle BCD, and the angle of angle C, the measure of that angle, is half the measure of the arc going from B to A to D. Well, if you add those two angles together, their measures together, then you're going to get half of what you get if you add these two arc measures together. Well, if you add those two arc measures together, you get 2 pi, or 360 degrees. Divide that by 2, and you get the sum of these two, which is 180 degrees, or pi radians. And so we see that these are supplementary, and you get exactly the same idea here. In fact, actually, because of the whether it's cyclic or not, if you get any two angles that are supplementary, whether they're opposite or consecutive, the other two pair have to be supplementary as well, because all four of them add up to 2 pi, or 360 degrees. And so when you add two of them together, if that's already pi, subtract that from 2 pi, the other two have to add up to pi as well. So so we get that result as well there. So that's interesting setup. Okay. So it turns out that if we look at supplementary angles, if it has a pair of opposite supplementary angles, then it has to be cyclic, one we were just looking at, right? So it turns out it has to be opposite there. If they turn out to be supplementary and opposite, they have to be cyclic. And if it turns out to be supplementary and consecutive, it has to be a trapezoid. Let's talk about this one first. If these are supplementary, then the C property of parallel lines says interior angles on the same side of a transversal are supplementary if and only if you get a pair of parallel lines. So think of the lines containing AB and the line containing C and D as being full lines, and this BC make it into a full line as a transversal. Then you can see that these are interior angles on the same side of the transversal. They're supplementary, so this is a parallelogram. I mean, not a trapezoid. And same thing, these pair over here are going to be supplementary as well. Okay. Now, going the other direction, showing that this has to be cyclic, going the other way is a little harder, but not too bad. Let's take a look at that. Well, here, let's prove it this way. If you start with any quadrilateral, you can take three of the vertices, say A, B, and C. You can always make a circle that goes around them, right? Because we know every triangle is cyclic. So the question is this point D on the circle or not? If what? If you got a pair of supplementary angles, okay, that are opposite. Okay, so here's what we're going to do. We're going to take this quadrilateral that goes through A, B, C, or let's just take those 3 points. And if you take this angle that's at C here and go on out, someplace it's going to hit this circle. Let's call that point D prime. It's going to turn out D prime is the same as D, but we got to show that. Okay, wherever that hits out there on D prime. Now, because we've already proved that if a quadrilateral is cyclic, then it has to have opposite angles supplementary. That tells us that the quadrilateral ABCD prime is cyclic, and therefore both pair of opposite angles, say B and D, are supplementary, as well as A and C are supplementary. Okay, so let's think about what that says about D prime. Well, since angle A and angle C are supplementary, and to begin with, when you're using the point D, so the angle B, let's put it this way, the angle BAD prime is a supplementary angle to angle C, and the angle BAD and BAD prime both are supplementary to this. They have to have the same measure. Well, that means they have to be the same angle, and then that means this point D and D prime have to be the same point. So it has to be there. So we've proved that if it's an if and only if statement, right? If you have a cyclic quadrilateral, both pair of opposite angles must be supplementary, and the converse, if both pair of opposite angles are supplementary, or just even one pair because you get the other one for free, then the quadrilateral must be cyclic. All right, there's also some interesting things here when we look at the quadrilaterals contained by the diagonals here. I meant to say the triangles formed here. So I'm clicked on this similar triangles here, and we'll let X be where the diagonals intersect. And let's look at some angles formed here. And there's some interesting things going on here. Notice that this angle BCA intercepts this minor arc AB here. Well, so does this angle at D, the angle ADB. So I've got them marked with the green. those are going to be congruent angles because they intercept the same arc. They each have a measure, half the measure of that intercepted arc. Okay. You also have some similar things here for an angle at B and A intercepting this arc CD. So the angle CAD, that purple one, is congruent to this purple one here. That's CBD. They both intercept this minor arc CD. You've got some vertical angle pairs here that are congruent. The red angles are congruent here, where you go from CDB and ABD. Now, those two are not necessarily congruent. Okay, but now let's take a look at some things. So we do have some triangles that have all of the congruent parts. For example, this one right here, AXD and BXC. Okay, they have congruent measures. Okay, and so those two triangles must be similar. Okay, now I think I have the color coding correctly. So the blue angles are congruent, the green ones are congruent, the red ones are congruent, the light blues here and the orange are congruent, like that. So we see that this triangle here, CBX, is similar to the triangle DAX, and the triangle up here and down here are congruent, or not congruent. Those are similar triangles. Similar triangles here, ABX, and then what is this? DCX. Okay, so we've got two pair of similar triangles, these two here and these two here. See, that's going to work no matter where you put it there. So you get some interesting triangles there that are similar to each other. So that's another thing about these that gives you an interesting property about cyclic quadrilaterals. Okay, so that tells us several things about cyclic quadrilaterals. Here are some of the properties reviewing. Given a quadrilateral ABCD, let X be this intersection of the diagonals. There exists a single circumscribed circle through A, B, C, and D. The perpendicular bisectors of each side intersect in a common point S called the circumcenter, which is equidistant from each of the vertices, A, B, C, and D. Quadrilateral ABCD has both pair of opposite interior angles supplementary. Cyclic quadrilateral ABCD is convex quadrilateral, and we have some similar triangles. Triangle ABX is similar to triangle DCX, and ADX triangle is similar to triangle BCX. And the following are equivalent. Quadrilateral is cyclic. That means it has the circle that goes through all the vertices. The perpendicular bisectors of the sides intersect at a common point called the circumcenter. If you get one of those, you get the other. The quadrilateral has at least one pair of opposite supplementary interior angles. If you've got that, you've got the other two. And if you have triangle ABX is similar to triangle DCX, that's enough to make all of these true as well. Let's do that last one. Let's talk about how we got that last one from there to the others. We talked about the other direction. So once again, we're going to use something similar to what we did a while ago. We're going to start by taking triangle ABC and putting the circumscribed circle around that, and put a point D prime down here that's on that circle, so that D prime is also on ray CD. Okay? We want to show that D and D prime are the same thing. Okay? All right, so let's think about this a second. Okay, so from what we proved the other direction, we know if it's a cyclic quadrilateral, that this angle ABD is going to be congruent to the angle, or D prime, is going to be congruent to the angle ACD prime. Those two angles have to be congruent because they intercept this same arc over here. Okay, that's for the point D prime, which we know is on the circle. Okay, but wait a minute. That makes so this point D prime has to be on this ray B. This angle right here has to be the same as this one here, right? So that the red angles, that's A, B, D, and A, C, D, because they intercept the same arc, so they're congruent. I'm sorry, I should have said D prime in both of those cases. But now wait a minute, we know that this angle here and this angle are congruent by our hypothesis, okay, with it going through D. So that means that the point D prime is on the ray BD, but we already put ray D prime on the ray CD, and those points, those two rays, could only meet at one point. They meet at D prime, but they also meet at D. So D prime and D must be the same thing. And so that proves that if you have these pair of similar triangles here, ABX is similar to DCX, that's enough to make it cyclic, and it also makes the other pair of triangles similar there as well. All right, so that gives us some interesting results about cyclic quadrilaterals.